Alright, let's talk about Newton's third law. Let's start by talking about basic properties of interactions. The interactions that we're dealing with in physics are interactions between objects. So an interaction between two objects, say A and B, always affects both objects. It's never been observed that A experiences a force because of the presence of B, but B does not experience a force because of the presence of A. This never occurs in nature. Therefore, if, for example, we were to count, if we had some way of taking a picture of all of the atoms in the universe, all of the particles in the universe,
so that you could count the total number of forces in the universe,
we'll find that the number of forces is even. Every time there is an interaction between two objects, both objects are affected. That means that for every interaction between two objects, there are two forces due to that interaction. If A interacts with B, there's two forces because of that interaction. If B interacts with C, then there is two forces related to that interaction, and so forth. So the number of forces in the universe must be even at all times. Second important property about interactions between physical objects is that they're either attractive or repulsive. If A interacts with B, A and B either feel attracted to each other or A and B repel each other. It has never been observed an interaction in which, for example, objects A and B are neither attracted nor repelled, but maybe move in the same direction. This has never been observed. So forces always come in pairs, and the force between two objects is either attractive or repulsive. From the fact that the force is always attractive or repulsive, you can see immediately that forces that belong to the same interaction are always opposite in direction. If they're attractive, if A and B, for example, if B is attracting A and A attracts B, then the force that B puts on A is opposite in direction to the force that A puts on B. The same, of course, for the case of repulsive. If this is the force that B puts on A, and this is the force that A puts on B, those two forces are opposite in direction. Now, this seems kind of intuitive up to this point. Now, the non-intuitive part of this is that it turns out that whenever A and B are interacting with each other, the force that B puts on A is exactly equal in magnitude to the force that A puts on B. The magnitude of forces belonging to the same interaction is equal. To summarize, we can say that to every interaction between objects corresponds a pair of forces. These forces are called action and reaction, and they have equal magnitude but opposite direction. Alright, let's now use Newton's third law to solve a problem with multiple interactions between different objects. So I have a cat here that is sitting on a box that is sitting on the surface of the earth. So why don't we start by drawing x and y axes to do the free body diagram for each one of these objects. Let's start with the cat. The cat is in contact with the box, therefore there must be a force that the box is putting on the cat. This force I'm going to call NB on C, meaning the normal force that the box puts on the cat. This is the force that is going to prevent the cat from dropping through the box. The partner to this force is the force with which the cat pushes on the box. Since the box has to push up on the cat to hold its weight, then the cat is obviously pushing back on the box. The direction of that force should be opposite to the force that the box pushes on the cat. So we're going to call that force the normal force that the cat puts on the box. From Newton's third law, we know that since these two forces are members of an action-reaction pair, the magnitude of those forces should be equal. Another force acting on the cat is the gravitational attraction between the Earth and the cat. the Earth is attracting the cat. That puts a downwards force on the cat. Now, what is the partner for this force? The gravitational attraction between the cat and the Earth acting on the Earth must be a force that attracts the Earth towards the cat. Newton's universal law of gravitation guarantees that the cat is attracting the Earth also as much as the Earth is attracting the cat. So the attractive force on the Earth due to the cat must be pointing upwards. We're going to call it Fg of the cat acting on the Earth. Those two forces are members of an action-reaction pair, therefore they must have the same magnitude. Now we're done with the forces acting on the cat. Now let's move on to the box. We already have one of the forces acting on the box. Another one is due to the contact between the box and the floor, the surface of the Earth. Since there is a contact between these two objects, there must be a normal force between them. The Earth is pushing on the box, and it has to do so to prevent the box from breaking through the surface of the Earth. That force must have a partner, according to Newton's third law, and that partner force must be acting on the Earth. It is the normal force that the box puts on the Earth. Once again, these two forces are an action-reaction pair, therefore their magnitudes must be equal. The final force acting on the box is the gravitational attraction between the box and the Earth. The Earth is attracting the box. That puts a force downwards towards the center of the Earth. We're going to call that force of gravity of the Earth acting on the box. Now the partner to this force is the force with which the box attracts the Earth. Since the Earth attracts the box attracts the Earth back. That force must be acting on the Earth, and it must be in the upward direction, towards the box. Once again, those two forces are members of an action-reaction pair, therefore their magnitudes must be equal. So now we have completed all of the forces in the free body diagrams for each one of the objects involved in this problem. Having done the free body diagram, we can proceed to write Newton's second law acting on each one of these objects. So let's start with the cat. We have two forces acting on the cat. One is positive, the other one is negative. So in magnitude, we can write that the normal force between the box and the cat in magnitude should be equal to the magnitude of the gravitational attraction acting on the cat, which is clearly the mass of the cat times g. So that tells us that the box must be pushing on the cat with a force exactly equal to the weight of the cat. The surface of the box has to support the weight of the cat to prevent it from breaking the surface. For the box, we have similarly that the only positive force, which is the normal force that the Earth, the surface of the Earth, has to put on the box, should be equal to the sum of the two forces pointing down. Remember that I'm writing here the magnitude. The letters represent the magnitude of the corresponding force vectors. So the normal force that the Earth puts on the box should be equal to the sum of the gravitational force acting on the box plus the normal force that the cat puts on the box. The gravitational force acting on the box is simply the mass of the box times g. Now, the normal force that the cat puts on the box, according to Newton's third law, should be equal to the normal force that the box puts on the cat. And from the equation above, we can see that that should be equal to the mass of the cat times g. So we can replace simply at the term the mass of the cat times g, which tells us that the normal force that the Earth has to put on the box is equal to the sum of the weights of the box and the cat, which I hope makes complete sense. The force with which the floor has to be pushing on the box to prevent it from moving through the floor is equal to the weight of the box plus the weight of the cat, since the cat is sitting on top of the box. That makes sense. The normal force that the box puts on the cat is only equal to the weight of the cat. Now if we look at the free body diagram for the Earth, we can write an equation for the normal force that the box puts on the Earth. This force should be equal to the sum of the upward going forces, so it should be equal to the gravitational force that the box puts on the Earth plus the gravitational force that the cat puts on the Earth. From Newton's third law, these forces must be equal to the mass of the box times g and the mass of the cat times g. So finally, we conclude here that the normal force between the box and the Earth that the box puts on the Earth, this is the force with which the bottom surface of the box is pushing on the floor, is equal to the weight of the box plus the weight of the cat. One more time, this makes complete sense.
In fact, we didn't have to calculate this force explicitly because
the normal force that the box puts on the Earth should be equal to the normal force that the Earth puts on the box. And that quantity we calculated before.